So in this video of chapter number 10 circles, we are going to see an important concept and very interesting concept which is called as angle subtended by a chord at a point. Okay, so first of all, let's see what is a chord, because we have seen this in the previous videos. What is the exact definition of chord? We're just going to quickly draw a circle here. So this is our circle. Okay, chord is nothing but take any two random points. So let's say this is a random point P and this is a random point Q on the circle. Chord is nothing but a line segment which join these two random points on the circle P and Q. So I'm going to join these two line segments P and Q. That's it. So this line segment PQ is called as a chord of the circle. Quite simple and straightforward. Now, angle subtended by a chord. So this chord is going to subtend an angle where? At a point. Okay. So let's take a point. Let's take this random point here. Let's call it X. Let's take this random point here. Let's call it Y. Now let's try to zoom in a bit. Yes. So angle subtended by this chord PQ at this point X or at this point Y is called as the angle subtended by the chord at any point on the circle. So how does that look like? Is basically we're going to connect these points. So P will be connected to X, okay, and this Q will also be connected to the X. So this angle, So this angle is called as the angle subtended by the chord PQ, okay, at the point X. Very similarly, we have this point Y here. So X is on this major arc, okay, whereas Y is on the minor arc. Doesn't matter, major arc, minor arc. It's basically an angle subtended by this chord on the circle. So let us quickly draw these things as well. This is the angle subtended at point Y. Okay, this angle. So this is that angle. Okay. Now, is it necessary that the point where the chord will subtend the angle should be on the circle? Not necessarily. You can also have a point inside the circle and still this chord PQ will subtend the angle. So very similarly, I'm going to draw another circle here. So let's draw another circle. Yes. So this is another circle. And once again, let's have these chords P and Q. Sorry, this points P and Q. So this is my point P, this is my point Q, and let's draw okay, let's draw this chord PQ. So this is our chord PQ. Now we are going to focus on the center of a circle. So this, let's call this as the center of the circle. Let's call it O. So O is the center of the circle. Now, if I want to find the angle subtended by the chord PQ at the center of the circle, all I have to do is same as before, just connect these lines. Okay. So from P you draw a line to O, which is the center. From Q also you draw a line to O, which is the center of the circle. So this angle now becomes the angle subtended by the chord PQ at the center of the circle O. Okay. So once again, quickly to see what is this definition, or what is this concept rather, of angle subtended by a chord at a point. So there are two possibilities. Either the point is on the circle, okay, like this X and Y. So this becomes that angle, this becomes that angle, or another possibility is the point is the center of the circle. So then this becomes the angle subtended by the chord at the center of the circle. Now, next we are going to see a theorem, very interesting theorem, which is related to this scenario where the chord subtends an angle at the center of the circle. So let's come down here. Yes, I already have a figure in place, but first we will see what the theorem reads. So let's bring the theorem in the focus. Okay, let's read this theorem. Equal chords of a circle subtend equal angles at the center. Okay, so this is my circle here. This is one chord AB, this is one chord PQ. Now the key thing is, let me highlight the keyword, that these chords are equal chords, okay, which means that their length is equal. So PQ is equal to AB, okay. That is a very important characteristics of these two chords, that their lengths are equal. So the theorem reads that if the chords are equal in length, then the angle that they both will subtend at the center is also equal angle. So this is what the theorem says. Now the thing is, it's a theorem, so we have to prove the theorem. The proof is very simple and straightforward. I am going to start writing here. So in the given circle, I'm just going to write here, in the given circle, okay, Now OP is equal to OQ. Okay, let me use a highlighter. So this OP, okay, is equal to OQ, which is equal to OA, which is equal to OB. Okay, why so? Because they all are radius of the circle, radius of the same circle. Okay, so OP is equal to OQ, which is equal to OA, which is equal to OB. All these four line segments are the radius of the circle. They are starting from the center of the circle and they go to the end point of the circle. So this is the very definition of the radius of a circle. So I'm just going to erase this. Okay, so all these four line segments, which are the radius of the circle, are equal to each other. Okay, so now the proof becomes very simple and straightforward. Basically, let's use point number 2. In triangle OPQ, so once again let me use a highlighter. So this triangle OPQ, okay, and and triangle OAB, so let's use another highlighter. So in triangle OAB, this triangle, okay, we have okay, so we have OP as equal to OA. Okay, so this is the thing. OP is equal to OA. Then we will have OQ as equal to OB. Okay, so OQ will be equal to OB, and finally we have PQ as equal to AB, because they are equal chords. This is a given information. This is given. Okay, and this is from 1. Okay, this statement number 1, we showed that all these four are equal to each other. So thus now, so thus from, or okay, let me do one thing. Let me go to the other side. Okay, let's come here. Let's try to zoom in. Thus, using, okay, side test of congruency, okay, we can say that triangle OPQ is congruent to triangle OAB. Okay, quite simple and straightforward. Using the side test, all the three sides of this triangle are equal to all the three sides of this triangle, which means these two triangles are congruent to each other according to the SSS test of congruency. Okay, and then from this it follows that is angle POQ is equal to angle AOB. Okay, this angle, okay, POQ will be equal to angle AOB. Why? Because, yes, so this is very important, because they are corresponding parts of congruent triangles. I'm going to write the full form here. Corresponding parts of congruent triangles. Okay, got it? Very important that this angle, let's zoom out. Okay, this angle POQ is equal to angle AOB because they are corresponding parts of congruent triangles, these congruent triangles. And that's it. We have proved our theorem. Let's come back to the theorem. The theorem reads that equal chords of a circle subtend equal angles at the center. So yes, these angles which are subtended by these chords, equal chords, are equal to each other. So thus a very simple and straightforward theorem, but also very interesting and important theorem which we'll be using to prove lots of exercises, unsolved problems in the future. Also note that how we are using the congruency of triangles in order to prove this theorem. So this is very important in throughout the chapter of circles. We are going to use different tests of congruency of triangles to prove that how the triangles are congruent to each other, and thus a lot of interesting properties come out. Now we also have a converse of this theorem. So let's come down here. The same figure we have, but here we are going to prove the converse of the theorem. What is the converse of the above theorem? Let's read the statement. If the angles subtended by the chords of a circle at the center are equal, okay, so in this case this is given that this angle is equal to this angle. Okay, let me mark it nicely. Okay, this angle is equal to this angle. If this is given, then the chords are equal. So now we'll prove that the chords are equal, PQ and AB. In the previous scenario, it was given chords are equal. So we proved the angles subtended are equal. Now converse is, if the chords are, sorry, if the angles subtended are equal, then prove that the chords are equal to each other. Once again, we are going to use test of congruency of triangles, and the process or the flow is very same. First of all, we know that OP is equal to OQ is equal to OA is equal to OB. Why so? Because they are all the radius of the circle. So first of all, OP is equal to OQ is equal to OA is equal to OB. Okay. Why? Because they are the radii of the same circle. Okay. Radii of the same circle. This is point number one. Now once again, in triangle POQ and triangle AOB, okay. So we have, so I'll say point number one, we have OA as equal to OP. Okay. Secondly, we have angle POQ as equal to angle AOB. Why so? Because this is given. The angles are equal to each other is given. And thirdly, we have let's say okay, we have OQ as equal to OB. Again, the radius of the circle. So if you note in these three steps, this is side, angle, side. Okay, the angle is included in the two congruent or two equal sides. So side and then this angle and then this side is equal to side and then this angle and then this side. Okay, so once again, here we are going to use a congruency test, and that is going to be SAS. Thus, by side angle side test of congruency, we say, okay, what do we say? That triangle OPQ or POQ, doesn't matter. So triangle POQ is congruent to triangle AOB. Okay. So here we have used SAS. I'm going to highlight this. Here we are going to use SAS test of congruency, and we have proven that this triangle is congruent to this triangle. And thus, from this, that is, from this we conclude that PQ is equal to AB. Once again, I'm going to highlight this PQ is equal to this AB. Why? Because they are corresponding parts of congruent triangle. This same, this is very important. I'm going to copy this. This is the reason, corresponding parts, okay, corresponding parts, copy, of congruent triangles. I'm just going to paste it here, paste. This is the reason for PQ as equal to AB. So thus, we have proven the converse of the theorem that, okay, if the angles subtended by any two chords, these were the any two random chords on the circle, but the angles that they subtended on the center were equal to each other, and if the angles subtended are equal, then the chords are also equal in length. That is what the theorem asks, and we have proved it. This was the converse of the previous theorem. Okay, this one. So thus we saw an important concept, which is the angle subtended by the chord at any point, and how the angles subtended at the center by equal chords are always equal to each other. That's it.